You need to learn about chemical reactions. So in a chemical reaction, we have one or more substances that are converted into one or more new substances. A chemical reaction always involves chemical changes. So we have rearrangement and exchange of atoms to make new molecules, but the atoms themselves are unchanged. The atoms are like Lego bricks, and in a chemical reaction, we're taking apart the thing we had before, and we're building new things using all the same Lego blocks. A combustion reaction is a particular kind of chemical reaction, and that's characterized by a substance combining with oxygen to make one or more oxygen-containing compounds. Combustion reactions produce heat, and that heat is very useful in supplying energy needs for our society. So a chemical equation is a shorthand way of describing chemical reactions. The general form is that you have the reactants on the left and an arrow pointing to the right, and those are the products. So the reactants are going to react to produce the products, right? There's more information in here. We're going to have the formulas and states of reactants and products. These are called state symbols. We often see these after the formulas in chemical equations. G means that substance is in the gas state, L is liquid state, S is solid state, and AQ stands for aqueous, meaning it's dissolved in water, a water solution. The equation is also going to give us the relative numbers of reactant and product molecules. And we can use those equations to figure out the masses of reactants that get used and the masses of products produced. So let's talk about burning methane. So methane gas has this formula, CH4, in the gas state, and it's going to react with oxygen gas to produce carbon dioxide gas and water in the gas state. Anytime something is combusting or burning, it combines with oxygen. So you may be asked to write a reaction for something burning, and they may not mention that oxygen is a reactant. You're supposed to know that. In order to burn, something has to have oxygen, right? That's how you put out a flame, is you suffocate it, you keep the oxygen in the air away from it. So if we look at this equation here and think about, well, what are these atoms doing, the individual Lego blocks? Over here, there are 2 oxygen atoms, but then in the products, there's 2 oxygen atoms here and another one over there. Could we make 3 oxygen atoms out of 2 oxygen atoms? No, we can't do that. So that's a problem. Another problem is the hydrogens. Over here, there's 4 hydrogens, and over here, there's only 2. Can we take 4 hydrogen atoms and make them into 2? Or maybe the 2 hydrogen atoms turn into the oxygen atom. No, it doesn't work like that. So this equation is not quite right because it violates the law of conservation of mass. So to fix this, we say we're balancing the equation. So we're adding coefficients, which are numbers in front of the chemical formulas, so that we have the same number of atoms of each element in the beginning and the end. So we can change the coefficients. We cannot change these subscripts, okay? The subscript is part of the chemical formula. You mess with that and you change the substance. Putting a 2 in front of it just tells me I have 2 molecules of that. So we can do that. So here we have our little round blocks shown. So methane has 1 black one and 4 white ones. Oxygen's 2 red ones. And in order to balance this, we're going to make there be 2 of these molecules. And then over here, we're going to get CO2. That's where the carbon went. And this is where 2 of the oxygens went. And then over here, we need to have 2 water molecules. Those are the other 2 oxygens, and there are the 4 hydrogens. So by adjusting the relative numbers of reactants and products, we can make it work so that all the atoms have a place to go. We don't have to steal any from somewhere else. Any questions about that?
Wouldn't you have like an extra oxygen still, or?
No, we don't have an extra oxygen still because here we've got two O2s. So there's 1, 2, 3, 4 of the red ones. And then there's 2 over here and 2 over there. Okay? Yeah. I really like this picture, and I really want you to look at this and ask me questions if it's not clicking for you. Because once you get that image in your mind of what's happening, then balancing equations is not such a weird thing, right? We're just trying to make it work out so that we don't have any blocks left over at the end, okay? Okay, so let's practice counting atoms in a chemical equation. We have to be able to count the atoms before we can balance them. So this is asking how many oxygen atoms are on the right-hand side of this equation. So the right-hand side means to the right of the arrow. So this 2 means that I have 2 of these units. So how many oxygens are in there? 6, right? Because each of these units has 3 and there's 2 of them. And how many oxygens over here in 4 CO2s? 8. And so 6 plus 8 equals 14. Okay? How many oxygens are on the left side? And we got 4 FeCO3. So 4 times 3 is 12. And here I have an O2, so that's 2, right? And 12 plus 2 equals 14. That's what we're trying to do when we balance a chemical equation. We're going to make the number of oxygens be equal on each side, the number of carbons, the number of irons, whichever elements are in the equation. So balancing chemical equations is something that can be approached in more than one way. And so here's a suggested guide. Start by writing out the skeletal equation. Meaning we need the formulas for the reactants and the formulas for the products and the arrow in between. Then what we want to do is we want to balance the atoms. So one approach is to balance atoms that occur in more complex substances first, and always leave atoms that are in pure elements until the last. So we want to balance atoms that occur as free elements last. And the reason for that is when we put a coefficient in front of an element, we're not going to mess up anything else. Whereas when you put a coefficient in front of a compound, then you're changing all of the elements in there. It's possible to end up with fractional coefficients. You can also completely avoid doing that, but if you end up with fractions, you need to get rid of them by multiplying the entire equation by the denominator of the fraction, and then we should always check at the end. So let's practice. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. Okay, so we need a skeleton. That means we need the formulas for these different reactants and products. So we've got solid silicon dioxide and, that's plus, solid carbon to produce, is the arrow, solid silicon carbide and carbon monoxide gas. So this is a sentence describing this chemical reaction. We're going to write it as a chemical equation, which is a shorthand sort of way. So silicon dioxide, practice our nomenclature a little bit. Is silicon a metal? No. So this would be named as a molecular compound. Silicon dioxide would be SiO2, right? Because there's no prefix on silicon and there's a prefix of 2 on the oxide, so that's 2 oxygens. And this is telling me that it's a solid. Plus solid carbon. So that's an element, right? Is it one of the diatomic elements? Horses need oats for clear brown eyes. There's a C in there, but the C is Cl. So no. Carbon, we just write C. If it was a diatomic element, then we have to put a 2 subscript. So this is also a solid. And we have an arrow. And then we have silicon carbide. Well, we already decided that, or established, that silicon is a nonmetal, or at least it's on the nonmetal side of the line. So we're going to have silicon, and carbide comes from carbon. And it doesn't give us a mono prefix anywhere, but it doesn't give us any other prefixes. I would not ask you this one on an exam because I don't think that's fair, but here it is. It used to be fun because I could ask Siri what the formula for silicon carbide was, and she'd say the formula is SiC. S-I-C. She doesn't say it anymore. It's really disappointing. Anyway, that's also a solid. Happy memories of times gone by. Plus carbon monoxide gas. So also a molecular compound. So carbon monoxide, there's 1 oxygen. And it says mono because there's also carbon dioxide, so they want to be clear about that. And this is also gas. Now we need to balance this. For most equations, you can use what's called balancing by inspection, where you just start looking at it and you kind of figure it out. It's like, well, those aren't very good instructions. Well, start with the first element. So how many silicons are on the left side? 1. And how many silicons are on the right side? 1. Okay, cool, that one's all fine. How many oxygens on the left? 2. And how many on the right? 1. How can we fix that? If we make there be 2 carbon monoxides, now there'll be 2 oxygens, right? Did that mess up the silicon? No, it didn't affect the silicon. So I've got 2 oxygens and I've got 2 oxygens. And now the carbons. This one's nice for the end because I can fix the carbons by putting a prefix or a coefficient here and it's not going to mess anything else up. So I've got 1 carbon here. How many carbons on this side? 3. There's 1 in silicon carbide and there's 2 in the carbon monoxide, so a total of 3. So I can put a coefficient of 3 in front of C, and that's only going to change the carbon and not going to mess up everything else. If I started with C and ended up with oxygen at the end or something, then I might get into a problem where I keep having to change things over and over again. If you start to feel like you're going in a loop, just stop and start over from a different place. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. A lot of gases here. So we have ethane, oxygen, carbon dioxide, and water. Combines with, it's a plus, to form is the arrow, and is the other plus. So it doesn't say the reactants are these and the products are those. It describes what's happening. Well, they gave us the formula for the first one because they don't really expect us to remember that one yet. And that's a gas. That's ethane. It's got 2 carbons. And so then I'm going to have a plus. I leave a space here because I know I might need to put a coefficient in there. And then the other reactant is oxygen. Is oxygen a diatomic element? Yes, it is. And so we have to write O2. If you write O, Mastering Chemistry is going to say it's wrong. And then we've got gaseous carbon dioxide. So that's carbon and 2 oxygens, which is a gas. And water, H2O, gas. Well, let's start looking at this. I've got a total of 2 carbons on the left, yes? And I have 1 carbon over here. So I could fix that by putting a 2 here. Now I've got 2 carbons and 2 carbons. Next I can look at the hydrogens. There's 6 hydrogens here. And I have 2 hydrogens in this water molecule. So how many water molecules do I need so I can have 6 hydrogen atoms? 3. Okay, now we've balanced everything except the oxygen. Oxygen's last. So this is where we can mess with oxygen and balance things and not mess everything else up. So let's look at how many oxygens are over here. 2 CO2s gives us how many? 4, right? And 3 H2Os gives me 3. So that's a total of 7. Over here, though, the oxygens are coming in pairs. So this is where you could use a fraction. You could say, well, I need 7 halves of O2, and that'll give me 7 oxygen atoms. Most students don't like that, so we're not going to talk about that. This is what I call the odd-even problem. I need an odd number of oxygens over here, but these are coming in pairs of 2, so I can only get an even number. You can make an odd number into an even number if you multiply by 2, right? So I'm going to multiply all of these coefficients by 2. So I'm going to put a 2 here. That's the one I'm working on. And so I'm going to change this to a 4, and I'm going to change this to a 6. So let's count these oxygens again. I have 8 now, and 6 is 14. So how many pairs do I need to get 14? 7. Because I doubled all of these, I did not mess up the balancing of the hydrogens and the carbons. And when I put a coefficient here, I'm only fixing the oxygens and not messing anything up. And then you should always check. Go through and count them up again. Any questions?
Would it just double every time, or is there any situations where it's you multiply by something else?
It's a good question. Would it always be double, or would you have to multiply by something else? I don't think I've ever seen an equation in Chem 1A where you'd have to multiply by something else. Okay, here's another one. This is one where we have ionic compounds with polyatomic ions. Write a balanced chemical equation for the reaction between aqueous lead to nitrate. So that's one thing. And aqueous potassium chloride to form, oops, that's too long, solid lead 2 chloride, wrong pen, and aqueous potassium nitrate. We're kind of combining, reviewing nomenclature and writing balancing equations here. On the exam for chapter 4, I'll give you an unbalanced equation and ask you to balance it. I'm not going to make you come up with all the formulas right away. Okay, so aqueous lead 2 nitrate. What kind of a compound is that? Acid, molecular, or ionic? It's ionic, right? Because lead is a metal. The Roman numeral is a giveaway also. So to write this formula, I need the formula for both of the ions with their charges. So I'm going to write that down below. So lead 2 means lead 2 plus. It tells me what the charge is. And then what's the formula for nitrate ion? NO3 -1. Okay, so then I have to figure out, well, how do I put those two together? Well, I'm going to need 2 of those guys, right? So this is going to be Pb NO3 2, and it tells me it's aqueous. Plus potassium chloride. So potassium is K. What's the charge? +1, because it's in group 1. And what's the charge on chloride ion? -1, because it's 1 over from the noble gases. So those are equal and opposite, right? So that's just KCl. We have a state symbol that we need, aqueous. And then we have lead 2 chloride. So that's going to be Pb Cl2, and it says that that's a solid. And aqueous potassium nitrate, so that's K plus and NO3 minus. Look at that. Pb2 plus is on both sides, and nitrate is on both sides. And potassium, wrong marker. Potassium and chloride. So this nitrate ion, it's a polyatomic ion, and what happened to it is it just changed partners. It did not come apart into nitrogens and oxygens and make something different. It stayed together. And so when we have polyatomic ions that stay together, we can balance them as a unit instead of counting all of the elements individually. So on the left side, how many lead ions do we have? 1. And how many over here? 1. So far, so good. How many nitrates? 2. And how many over here? 1. So I need to put a 2 in front of that one, so I can have 2 nitrates. And then I'm just moving along on the reactant side, and I get to potassium. How many potassiums over here? 1. And how many over here? 2. So I need to put a 2 here. And then chlorines, 2 chlorines and 2 chlorines. Any questions? So we could think of it this way. So 2 KCl and PbCl2 and 2 KNO3. So these nitrate ions just ended up over here. The potassium's the same number. You see how that is? The ions are just switching places. I have a fun analogy for that later.